The dream is seductive. Shining cities under geodesic domes, settlers terraforming a new world, humanity becoming a multi-planetary species, ensuring our survival against cosmic catastrophes. Elon Musk promises 1 million people on Mars by 2050. NASA plans crewed missions in the 2030s. The enthusiasm is infectious, the vision inspiring. But here's what nobody wants to tell you. We're probably never colonizing Mars. Not in your lifetime, not in your grandchildren's lifetime, possibly not ever. Today we're going to examine the hard truths that space agencies whisper about but rarely shout, the reasons why the red planet might remain forever beyond our reach as a true second home for humanity. If you're fascinated by the realities of space exploration, make sure to subscribe to this channel and give a thumbs up. And one quick question: if you could send a message to an alien civilization, what would you say in just one sentence? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with the most fundamental problem. Mars is trying to kill you from the moment you arrive. The thin atmosphere, composed of 95% carbon dioxide, has a surface pressure of just 600 pascals, less than 1% of Earth's atmospheric pressure. This isn't like standing on top of Mount Everest. This is a vacuum so extreme that your saliva would boil at body temperature. Any tear in your spacesuit, any failure in your habitat's pressure seal, and you have seconds, not minutes, before unconsciousness, followed shortly by death. But the atmosphere's thinness creates a cascade of other problems. Without a thick atmosphere, Mars has no protection from radiation. Earth's atmosphere and magnetic field shield us from cosmic rays, high-energy particles from supernovae and other violent cosmic events, and from solar radiation. On Earth's surface, you receive about 0.3 millisieverts of radiation per year from cosmic sources. On Mars, you'd receive about 250 millisieverts per year, over 800 times more. This isn't a minor inconvenience. This is cancer-causing, DNA-damaging radiation that would bombard every cell in your body every moment of every day. The Mars Science Laboratory, Curiosity rover, has been measuring radiation on Mars since 2012. The radiation assessment detector found that during the cruise from Earth to Mars, astronauts would be exposed to about 300 millisieverts. On the Martian surface, the annual dose would vary with solar activity, ranging from 200 to 400 millisieverts per year, depending on solar storms and cosmic ray flux. To put this in perspective, radiation workers on Earth are limited to 50 millisieverts per year by safety regulations. A 6-month stay on Mars would expose you to more radiation than is considered safe for an entire career as a nuclear power plant worker. Some propose building habitats underground to shield colonists from radiation. This sounds reasonable until you consider what that actually means. You're not just digging a basement. Effective radiation shielding requires several meters of regolith, Martian soil, above you. This means excavating enormous volumes of rock-hard, frozen ground with equipment that must be transported from Earth or manufactured on Mars from raw materials. The energy requirements alone are staggering. Let's talk about that energy for a moment. On Earth, we take energy for granted. Flip a switch and lights turn on. On Mars, every single joule of energy must be generated, stored, and managed with ruthless efficiency. Solar panels work on Mars, but they're far less effective than on Earth. Mars receives only about 43% of the sunlight that Earth does, and frequent dust storms can block sunlight for weeks or months. The global dust storm in 2018 darkened skies so much that the Opportunity rover, which had operated for nearly 15 years, couldn't generate enough power to survive. It never woke up again. Nuclear power seems like the obvious solution, and indeed missions like Curiosity and Perseverance use radioisotope thermoelectric generators, RTGs, which convert heat from plutonium decay into electricity. But scaling this up to power a colony presents problems. Plutonium-238, the isotope used in RTGs, is expensive and scarce. The United States produced only about 1.5 kilograms per year at peak production, and global stockpiles are limited. A Mars colony would need megawatts of power, not the 100 watts that an RTG provides. Building nuclear fission reactors on Mars is theoretically possible, but you'd need to transport the reactor, the fuel, and all the infrastructure, or mine and process uranium on Mars. Both monumental challenges. The psychological effects of living in a radiation shelter, underground or in heavily shielded habitats, for years or decades, cannot be overstated. Humans evolved under open skies with natural light cycles. Studies of Antarctic research stations, submarines, and the International Space Station consistently show that isolation, confinement, and lack of natural environments cause depression, anxiety, interpersonal conflicts, and cognitive decline. Now imagine that environment, but you can never go outside without a spacesuit, never breathe fresh air, never feel rain, never see a blue sky. And unlike Antarctic researchers who can leave after a tour, Mars colonists would be trapped. Return trips to Earth require waiting for orbital alignments and would take 6 to 9 months. The communication delay between Earth and Mars ranges from 4 to 24 minutes one way, depending on planetary positions. This doesn't sound terrible until you realize what it means in practice. Every conversation with loved ones on Earth involves waiting 8 to 48 minutes between question and answer. Every emergency requires you to solve it yourself because by the time you ask for help and receive a response, the crisis may have killed you. Every technical problem must be diagnosed and repaired with whatever resources you have on hand, because ordering replacement parts means waiting months or years for the next supply ship, if one is even scheduled. Now let's address the financial nightmare that is Mars colonization. The Apollo program, which put 12 people on the moon for a combined total of about 300 hours, cost approximately $150 billion in today's money. The International Space Station, which maintains a crew of 6 to 7 people in low Earth orbit, just 400 kilometers above Earth's surface, accessible within hours if something goes wrong, has cost over $150 billion over 2 decades, with annual operating costs of $3 to $4 billion. And we're talking about colonizing Mars. Elon Musk's SpaceX estimates that developing Starship and making Mars colonization feasible might cost $10 billion. Let's be extraordinarily generous and assume they're right. Now consider what a colony actually needs: habitats, life support systems, power generation, water extraction and purification, food production, medical facilities, manufacturing capability, communication systems, radiation shielding, spacesuits, rovers, and countless other systems. Then consider that every kilogram of mass sent to Mars costs thousands of dollars in fuel and equipment. A single Starship launch might carry 100 tons to Mars, but a self-sustaining colony would need thousands or tens of thousands of tons of equipment. But even those numbers hide the real cost: maintenance and resupply. Machinery breaks, electronics fail, seals wear out. Without a continuous stream of replacement parts, spare components, and new equipment, the colony would slowly degrade. The ISS requires regular resupply missions. Cargo ships arrive every few months carrying tons of supplies, spare parts, and equipment. Mars colonists would need similar support, but the missions would take 6 to 9 months each way and could only launch during specific windows every 26 months, when Earth and Mars align favorably. Let's run the numbers on food alone. An adult human needs about 2,000 to 2,500 calories per day. Growing food on Mars means farming inside pressurized, heated, lit greenhouses using Martian soil that contains perchlorates, toxic salts that would need to be removed, and adding nitrogen, which is scarce on Mars, plus all the organic matter that makes soil fertile. The equipment to do this at scale, LED grow lights, water pumps, heating systems, atmospheric control, would need to be transported from Earth or manufactured on Mars from raw materials that would also need to be mined, processed, and assembled using equipment transported from Earth. Some propose that Mars colonists could achieve self-sufficiency by manufacturing everything they need from Martian resources. This concept, called in situ resource utilization, or ISRU, sounds promising until you examine what it actually requires. Manufacturing even simple items, tools, pipes, wires, requires raw materials, smelting and forging equipment, energy, and skilled workers. Manufacturing complex items, electronics, computers, medical equipment, requires advanced facilities with clean rooms, precision tools, and rare elements that might not exist in accessible concentrations on Mars. Earth's industrial civilization didn't spring into existence overnight. It evolved over millennia, building on accumulated knowledge, infrastructure, and resources. We have mines extracting specific ores, refineries processing them, factories turning refined materials into components, other factories assembling components into finished goods, all connected by transportation networks and powered by energy infrastructure that took centuries to develop. The idea that a few hundred or even a few thousand Mars colonists could replicate this industrial base on a planet with no breathable air, no liquid water on the surface, no ecosystem, and crushing radiation strains credulity. The Mars Society and other advocacy groups often point to historical parallels: Antarctic research stations, the colonization of the Americas, the settlement of harsh environments on Earth. But these comparisons fall apart under scrutiny. Antarctic stations are supplied from Earth, just hours away by plane. If something goes catastrophically wrong, evacuation is possible within days. The colonization of the Americas occurred when the settlers could breathe the air, drink the water, and grow crops in the soil. Even the harshest desert or the coldest tundra on Earth is paradise compared to Mars. Water is another critical challenge. Mars has water ice, particularly at the poles and in permanently shadowed craters, and the Phoenix lander confirmed water ice just beneath the surface at high latitudes in 2008. But extracting, purifying, and distributing water on Mars requires energy and equipment. You can't just turn on a tap. You need to mine ice, melt it, purify it to remove perchlorates and other contaminants, and then store and distribute it through heated pipes that won't freeze in temperatures that routinely drop to -60°C at night and can plunge to -125°C at the poles. The Martian day, called a sol, is about 24 hours and 39 minutes, conveniently close to Earth's day. But the Martian year is 687 Earth days, and the planet's axial tilt of 25 degrees creates seasons similar to Earth's, though twice as long. This means that winter in Martian polar regions involves months of darkness and temperatures that drop to levels where carbon dioxide freezes out of the atmosphere, creating dry ice caps. Any colony would need to endure these extreme seasonal variations with no possibility of retreating to a more temperate climate. The low gravity on Mars, 38% of Earth's gravity, presents insidious long-term health problems that we're only beginning to understand. Astronauts on the International Space Station experiencing microgravity lose bone density at rates of 1 to 2% per month. Muscles atrophy. The cardiovascular system weakens because the heart doesn't have to work as hard to pump blood. After 6 months in space, astronauts return to Earth requiring weeks or months of rehabilitation to regain strength, and some effects might be permanent. Mars has gravity which should help, but we don't actually know how much. We have data on zero gravity from the ISS and 1 gravity from Earth, but we have no data on how human bodies adapt to 0.38 g over months or years. Some scientists speculate that Mars gravity might be enough to prevent the worst effects of microgravity, while others worry it might merely slow the degradation without stopping it. Children born on Mars would grow up in this reduced gravity, potentially developing weaker bones and muscles that might make them unable to ever return to Earth. They would be Martians in a very literal sense, adapted to Mars but perhaps unable to survive Earth's gravity. Pregnancy and child development in reduced gravity is completely unstudied. We don't know if human embryos can develop normally in Mars gravity. We don't know if the increased radiation exposure would cause birth defects or developmental problems. We don't know if children's bones and organs would form properly. These aren't minor uncertainties. They're fundamental questions about whether humans can actually reproduce and raise healthy children on Mars. Until we answer them, talk of permanent colonization is premature. Some propose rotating habitats to create artificial gravity through centrifugal force. This works in principle and might be practical for space stations, but on a planetary surface, it's enormously complex. You'd need massive rotating structures, sealed against the Martian atmosphere, powered continuously and maintained despite the mechanical stresses of constant rotation. It's not impossible, but it adds yet another layer of complexity and cost to an already staggeringly complex endeavor. The isolation of Mars creates unique psychological challenges that go beyond normal isolation. On Earth, even in the most remote locations, you're still on Earth, the same planet where humanity evolved, where rescue is at least theoretically possible. On Mars, you're on an alien world, separated from Earth by millions of kilometers of vacuum. Speaking of those vast distances, if you want to truly understand the scale of our cosmic neighborhood and why interplanetary travel is so challenging, check out my video, How Big is the Solar System?, where we explore the mind-bending distances that separate the planets. The link is in the description and on the card above. Now, even if we solved every technical challenge, radiation shielding, life support, food production, energy generation, manufacturing, we face a deeper problem. The economic model for Mars colonization doesn't exist. Who pays for this? SpaceX is a private company that must eventually generate revenue. NASA's budget is about $25 billion per year, and Congress frequently questions even that level of funding. The International Space Station partnership involves 15 countries pooling resources, and it costs $3 to $4 billion per year just to maintain. A Mars colony would cost orders of magnitude more than the ISS. Not millions, not billions, but potentially trillions of dollars over decades. Where does this money come from? Some suggest that Mars colonists would mine valuable resources and ship them to Earth. But what resources? Mars has the same elements as Earth, formed from the same stellar nucleosynthesis processes. There's no magic element unique to Mars. Precious metals might exist in certain concentrations, but the cost of mining, refining, and shipping them from Mars to Earth would vastly exceed their market value. Helium-3, sometimes proposed as a valuable fusion fuel, is actually more abundant on the Moon than on Mars, and we haven't bothered to mine it from the Moon because we don't have working fusion reactors that need it. And if we did, there are terrestrial sources and breeding methods that would be far cheaper than lunar or Martian mining. The economic justification for Mars colonization based on resource extraction is, to put it bluntly, fantasy. Others argue that Mars colonization is insurance against existential risks on Earth, asteroid impacts, nuclear war, pandemics, climate change. This argument has superficial appeal until you think it through. If humanity has the resources and technology to establish self-sustaining colonies on a radiation-blasted, airless, freezing desert world, we certainly have the resources to prevent or mitigate existential risks on Earth, which is vastly more habitable even after nuclear war or severe climate change. Earth, even in a worst-case scenario, would still have breathable air, manageable radiation levels, liquid water, and an ecosystem. Mars offers none of these. The backup drive for humanity argument also assumes that Mars colonies could survive if Earth civilization collapsed. But, as we've discussed, Mars colonies would depend on continuous resupply from Earth for decades or centuries until they achieve true self-sufficiency, if that's even possible. If Earth civilization collapsed, those supply missions would stop, and Mars colonies would likely fail within months or years. They wouldn't be backing up humanity, they'd be sharing its fate. Some space advocates propose O'Neill cylinders, massive rotating space habitats in orbit around Earth or at stable Lagrange points, as superior to Mars colonization. These habitats could provide Earth normal gravity through rotation, could be shielded from radiation by mass or magnetic fields, and could be positioned to receive full solar energy without dust storms. They'd be closer to Earth than Mars, allowing faster communication and easier resupply. Every problem that makes Mars difficult, low gravity, radiation, distance, lack of resources, could be addressed more easily with orbital habitats than with planetary colonization. The technological heritage of space exploration actually points away from planetary surfaces and toward orbital habitats. We've maintained continuous human presence in orbit since the International Space Station became operational in 2000, but we haven't returned to the Moon since 1972. This isn't because the Moon is harder to reach than low Earth orbit, it's because there's no compelling reason to establish permanent lunar bases with current technology and economics. If we can't justify Moon bases, which are only 3 days away and could be resupplied monthly, how do we justify Mars colonies that are 6 to 9 months away and can only be resupplied every 26 months? The Mars Direct plan, proposed by Robert Zubrin in the 1990s, attempted to address costs by using in-situ resource utilization aggressively. The plan involved sending a return vehicle to Mars ahead of the crew, using Martian atmospheric CO2 and hydrogen brought from Earth to manufacture methane and oxygen fuel through the Sabatier reaction. This reduces the mass that must be sent from Earth. It's clever chemistry and demonstrates that we can do useful things with Martian resources. But it doesn't solve the fundamental problems of radiation, low gravity, isolation, and the enormous costs of establishing and maintaining a permanent settlement. NASA's current plans for Mars involve the Artemis program first returning humans to the Moon, establishing a lunar gateway station, and using lunar missions to test technologies for Mars. The timeline keeps slipping. First it was the 2020s, then the 2030s. Now, some NASA documents hint at the 2040s. This gradual retreat in timelines reflects the reality that each new study reveals additional complications, each new requirement adds mass and cost, and each honest assessment concludes that we're further from Mars capability than optimistic projections suggest. The SpaceX Starship system, if it works as advertised, would be revolutionary for accessing space. A fully reusable rocket that can launch 100 to 150 tons to low Earth orbit would dramatically reduce launch costs. But even with Starship, the challenges of Mars colonization remain largely unchanged. Cheaper access to orbit helps, but it doesn't solve radiation exposure, doesn't create a breathable atmosphere, doesn't generate gravity, doesn't overcome communication delays, and doesn't provide the industrial infrastructure needed for self-sufficiency. Some argue that technological progress will solve these problems, that we can't imagine the solutions that future generations will develop. This argument appears throughout history, and sometimes it's right. But sometimes technologies that seem inevitable never materialize because they're not physically possible or economically viable. We don't have flying cars not because we lack the technology, but because they're impractical. They'd be expensive, dangerous, noisy, and inefficient compared to ground vehicles and aircraft serving separate niches. Similarly, Mars colonization might be something we can technically do but pragmatically shouldn't. The comparison to historical exploration and colonization breaks down in another crucial way: economics. European colonization of the Americas was profitable. Ships returned laden with valuable resources: gold, silver, tobacco, cotton, sugar. Later, the colonies became markets for European goods and sources of raw materials. This created a self-reinforcing economic cycle that funded further colonization. Mars offers no such cycle. Everything sent to Mars is an expense. Nothing returned from Mars would justify the cost of retrieval. The economic gravity well is entirely one-directional. Money flows to Mars and nothing flows back. Consider the counterfactual. What could we do with the $1 trillion or more that Mars colonization would cost? We could deploy massive solar and wind energy infrastructure, achieving carbon neutrality. We could fund fusion research until we solve it. We could build ocean desalination plants, solving water scarcity. We could develop closed-loop recycling systems, reducing resource extraction. We could fund education and research, creating technologies we can't yet imagine. All of these investments would improve life on Earth for billions of people, whereas Mars colonization would, at best, support thousands of people living in underground bunkers on a hostile world. The environmental case for Mars colonization sometimes argues that learning to terraform Mars would teach us to restore Earth's environment. But this is backwards. Earth's environment is damaged by human activity and could be restored by ceasing harmful activities and actively remediating damage, challenging but achievable with current technology and sufficient political will. Mars's environment isn't damaged, it's naturally hostile and would require planetary-scale engineering vastly beyond anything we've ever attempted. If we can't muster the will to solve environmental problems on Earth, where the stakes are immediate and the solutions known, why would we successfully terraform Mars, where the challenges are exponentially greater? Terraforming Mars, often depicted in science fiction, faces obstacles that might be genuinely insurmountable. Mars lost its magnetic field billions of years ago, likely due to its core solidifying. Without a magnetic field, the solar wind strips away atmosphere. Even if we could somehow generate a thick atmosphere by sublimating the polar caps, importing comets, or industrial production of greenhouse gases, the solar wind would gradually erode it unless we could restart Mars's magnetic field, which would require remelting the core. The energy required for this is beyond human civilization's current or foreseeable capabilities. Some scientists have proposed creating an artificial magnetic field at the Mars-Sun Lagrange point L1, which would shield Mars from the solar wind. Simulations suggest this might allow atmospheric pressure to build over decades or centuries, but the satellite required would need to generate a magnetic field strong enough to deflect the solar wind across Mars's entire diameter, requiring either impossibly large superconducting coils or power generation far beyond current technology. And this would need to operate continuously forever, because the moment it fails, atmospheric loss resumes. Even if we solved atmospheric retention, warming Mars to comfortable temperatures presents staggering challenges. The planet receives only 43% of the sunlight Earth receives. Simply melting the polar caps would release CO2 and water vapor, greenhouse gases that would warm the planet somewhat, but studies suggest this would only raise atmospheric pressure to about 12 millibars, still far below the 620 millibars needed for liquid water stability and nowhere near the 1,000 millibars of Earth's sea level pressure. Manufacturing additional greenhouse gases would require industrial facilities operating for centuries or millennia, consuming enormous amounts of energy and resources. Let's discuss Mars's magnetic field absence in more detail because it illustrates a fundamental problem with planetary colonization. Earth's magnetic field protects us from cosmic radiation and prevents atmospheric stripping by the solar wind. It's generated by convection currents in Earth's liquid outer core, an enormous self-sustaining dynamo that's been operating for billions of years. Mars is smaller than Earth, so it cooled faster, and its core solidified, shutting down the dynamo. This isn't something we can easily fix. Restarting planetary-scale geological processes is beyond human capability and likely will remain so for any foreseeable future. The romance of Mars colonization often invokes the pioneering spirit, the human drive to explore, the dream of new frontiers. These are powerful motivations, and I don't dismiss them. Humans have always pushed boundaries, explored new territories, and settled in hostile environments. But we've always done so when the new territories offered something: resources, opportunity, escape from persecution, the promise of a better life. Mars offers none of these. It offers only hardship, danger, isolation, and early death from radiation-induced cancer. Moreover, the frontier spirit narrative ignores that historical frontiers on Earth were often already inhabited, and colonization involved displacing or destroying indigenous peoples. Mars appears to be lifeless, but we haven't confirmed this conclusively. The Perseverance rover is currently collecting samples that will eventually be returned to Earth for analysis. If we discover that Mars harbors life, even microbial life, the ethical implications are profound. Would we have the right to colonize a planet with its own biosphere? Would introducing Earth life to Mars contaminate an independent genesis, destroying irreplaceable scientific insights into life's origins? The planetary protection protocols currently governing Mars missions try to prevent forward contamination, bringing Earth microbes to Mars, and back contamination, bringing Martian organisms to Earth. These protocols require extensive sterilization of spacecraft and careful handling of returned samples, but a Mars colony would, by necessity, violate these protocols completely. Humans shed millions of bacteria continuously. We can't live in sealed environments indefinitely without some exchange of air and material with the outside. A human colony on Mars would inevitably introduce Earth life to Mars, potentially threatening any native Martian life. Some scientists argue that Earth and Mars have been exchanging material for billions of years through asteroid impacts that eject rocks into space. Some of these rocks carrying Earth microbes eventually land on Mars and vice versa. If life exists on both planets, it might share a common origin: panspermia, the hypothesis that life seeds between planets naturally. This would reduce concerns about contamination. But we don't know if this is true, and the precautionary principle suggests we should be extremely careful until we understand Mars's biology, or confirm its absence, more thoroughly. The search for life on Mars adds another complexity to colonization timelines. Before we commit to large-scale human presence, we should thoroughly explore Mars robotically, searching for life in subsurface ice, in protected caves, in recurring slope lineae where liquid brines might exist. This robotic exploration could take decades or longer, especially since we're searching for microbial life that might exist in small, localized environments. Rushing to colonization before completing this search would be scientifically reckless. Let's talk about the psychology of Mars colonization volunteers. Who would go? Early proposals suggest volunteers would self-select from among the brave, the adventurous, those seeking to make history. The Mars One project, announced in 2012 and declaring bankruptcy in 2019, claimed to receive thousands of applications for one-way trips to Mars, but psychological screening for extreme isolation and confinement is imperfect at best. Antarctica has strict screening for winter-over crews, yet psychological problems still occur. The ESA's Mars 500 simulation, where 6 volunteers spent 520 days in isolation simulating a Mars mission, revealed interpersonal conflicts and psychological stress, despite knowing it was temporary and they could leave if truly necessary. A Mars colony would face worse conditions than Mars 500. The isolation would be permanent. Volunteers would die on Mars, never returning to Earth. The environment would be genuinely deadly, not simulated. The work would be grueling and never-ending, maintaining life support, growing food, repairing equipment, all while managing radiation exposure and health deterioration. The psychological toll would be immense, and we know from historical examples, isolated outposts, submarines on extended patrol, polar research stations, that even motivated, screened individuals struggle with such conditions. Suicide, depression, and interpersonal violence would be serious risks in Mars colonies. In isolated environments on Earth, these occur despite the knowledge that extraction is possible if things become unbearable. On Mars, there's no extraction. If you become suicidal, depressed, or dangerous to others, the colony must deal with it internally because there's no sending you home. The 6 to 9 month journey back to Earth isn't available on demand. It requires waiting for orbital windows, preparing a spacecraft, and enduring the long voyage. A colonist experiencing psychological crisis wouldn't have practical options. The medical challenges of Mars colonization extend far beyond radiation and low gravity. Every medical condition that occurs on Earth could occur on Mars, but treatment options would be severely limited. A Mars colony would need medical facilities, trained personnel, medications, surgical equipment, and diagnostic tools. But what happens when someone needs a procedure the colony isn't equipped for? On Earth, you can fly a critically ill patient to a specialized hospital within hours. On Mars, even knowing that a colonist needs urgent care that the colony can't provide means that person will likely die because there's no medevac to Earth. Childbirth, which even in modern hospitals occasionally requires emergency C-sections and specialized neonatal care, would be particularly risky. Infant mortality rates that humanity has reduced through advances in obstetrics and pediatric medicine would likely spike on Mars. Raising children in such an environment, where a medical emergency could be a death sentence, where they'd never breathe fresh air or feel rain, where radiation slowly damages their DNA, seems not just difficult, but arguably unethical. The legal and governance challenges of Mars colonies are often overlooked in technical discussions, but they're substantial. The Outer Space Treaty of 1967, ratified by over 100 nations including all spacefaring nations, states that outer space, including the Moon and other celestial bodies, is not subject to national appropriation. No nation can claim sovereignty over Mars. This creates ambiguity about governance. Who makes and enforces laws in a Mars colony? If SpaceX establishes a colony, does it govern itself? Are colonists subject to their nation of origin's laws? What happens in disputes between colonists from different countries? The lack of clear legal frameworks for space settlement isn't just an academic concern. It affects property rights, resource extraction, criminal justice, and basic governance. If someone commits a crime on Mars, who has jurisdiction? If a company extracts resources, who has the right to authorize this? These questions don't have agreed-upon answers, and international consensus on space law is difficult to achieve when nations have competing interests. Some commercial space companies argue for interpretations of space law that allow private resource extraction even if national appropriation is forbidden. The U.S. Commercial Space Launch Competitiveness Act of 2015 attempted to grant American companies rights to resources they extract from asteroids and other celestial bodies, but whether this is consistent with international law remains debated. Establishing Mars colonies without resolving these legal ambiguities invites conflicts that could range from diplomatic disputes to actual violence. The environmental ethics of Mars colonization deserve consideration. Even if Mars is lifeless, it represents a pristine environment that has evolved for 4 0.6 billion years without human interference. Some philosophers argue that Mars has intrinsic value beyond its utility to humans, that we have a responsibility to preserve it as it naturally exists. Colonization would irreversibly transform Mars, especially if we attempt terraforming. Is this morally acceptable? Do we have the right to transform an entire planet to suit our needs? These ethical questions become more urgent if we discover extinct or extant life on Mars. Mars was warmer and wetter in its distant past, with liquid water flowing on its surface and possibly an ocean in the northern hemisphere. If life arose during this period, remnants might persist in protected environments, deep underground, in ice deposits, or in isolated aquifers. Discovering Martian life, even fossilized, would be one of the most important scientific findings in history. Destroying it through colonization before we've thoroughly studied it would be an irreplaceable loss. The alternative to Mars colonization, focusing on Earth and near-Earth space, offers more practical paths forward. Earth observation satellites, weather monitoring, GPS, and communication satellites provide enormous value. The ISS has contributed to medical research, materials science, and our understanding of long-duration spaceflight, expanding orbital infrastructure, space stations, satellite servicing capabilities, space tourism, and eventually orbital manufacturing leverages advantages of space while remaining close to Earth. Asteroid mining, despite its challenges, makes more economic sense than Mars colonization. Asteroids contain metals and water ice. They're accessible with less delta V than Mars in many cases, and retrieved resources could be used in orbit for construction and life support without fighting a gravity well. The first asteroid mining operations would likely focus on water extraction for propellant production, enabling refueling depots that make deep space missions more practical. This infrastructure development could eventually support human presence throughout the solar system without requiring planetary colonization. The Moon offers a more practical stepping stone than Mars for learning about off-world settlement. It's 3 days away, not 6 to 9 months. Communication delays are seconds, not minutes, to hours. Return to Earth is possible within a week if something goes catastrophic. The lack of atmosphere is actually advantageous in some ways. No dust storms, easier vacuum operations, clearer vacuum conditions for manufacturing processes. The polar regions have water ice and areas of near-permanent sunlight, providing resources and power. If we can't establish sustainable lunar bases, we have no business attempting Mars colonies. China, India, Russia, and other nations are developing lunar programs, and international cooperation could build lunar infrastructure that benefits all of humanity. The Artemis Accords, initiated by NASA and signed by multiple nations, attempt to establish principles for lunar cooperation. While not without controversy, some nations critique them as US-dominated, they represent efforts to create frameworks for peaceful space utilization. Focusing on the Moon allows such cooperation to develop before attempting more ambitious projects. The technological development pathway through lunar settlement makes sense. Master life support systems on the Moon before attempting Mars. Develop radiation shielding techniques in a place where you can test and iterate quickly. Perfect in situ resource utilization where failed experiments don't doom colonists to death by asphyxiation or starvation months from rescue. Build the industrial capacity to manufacture complex items off-world before attempting to do so on a planet that's orders of magnitude farther away. Each lesson learned on the Moon increases the chances of success for eventual Mars missions, if they ever become justified. The romance of Mars has deep cultural roots. Science fiction from Edgar Rice Burroughs to Kim Stanley Robinson has portrayed Mars as a frontier awaiting human settlement. The idea that humanity's destiny lies among the stars is appealing, even inspiring. But inspiration shouldn't override careful analysis. The universe doesn't care about our dreams. Physics, biology, and economics constrain what's possible, and wishing doesn't change physical laws or create resources from nothing. The psychological weight of being the first Mars colonists, knowing you'll never return home, watching Earth as a bright star in the alien sky, is almost impossible to imagine. The first colonists would be pioneers in the truest sense, but also exiles, separated from everything familiar by an enormous gulf of space and time. The glory of being first might sustain volunteers through selection and training, but would it sustain them through years of grinding work in a dangerous environment where every mistake could be fatal? Some Mars advocates compare colonization to the Apollo program, arguing that if we could land on the Moon in the 1960s, we can certainly colonize Mars now, but this comparison misunderstands Apollo. NASA didn't colonize the Moon. They visited briefly, planted flags, and left. The entire Apollo program involved 12 people walking on the Moon for a combined total of about 300 hours. We haven't returned in over 50 years because the scientific and geopolitical motivations that drove Apollo, beating the Soviets, demonstrating technological superiority, no longer justify the expense. Apollo also operated in a very different economic and political context. It consumed nearly 5% of the federal budget at its peak, a level of funding politically impossible today. It was sustained by Cold War competition and the personal commitment of President Kennedy. Modern space exploration must justify itself through scientific return, economic benefit, or sustained public enthusiasm. Mars colonization offers uncertain science, no economic benefit, and public enthusiasm that might not survive the first deaths or the revelation of mounting costs. The first Mars colonists who die, and deaths are statistically certain given the hazards, will create a political and public relations crisis. When the Challenger shuttle exploded in 1986, killing 7 astronauts including teacher Krista McAuliffe, the American space program paused for years. When Columbia disintegrated in 2003, another 7 astronauts died, and again the program was grounded for extensive review. These tragedies occurred during routine operations with mature technology. Mars colonies would operate at the edge of capability with minimal redundancy. Deaths from equipment failure, medical emergencies, accidents, or even suicide would be likely, if not inevitable. How does a society react when colonists die on Mars? Do we continue sending people, accepting casualties as the price of expansion? Do we abandon colonization efforts after the first tragedy? These aren't hypothetical questions. They're foreseeable scenarios that need honest discussion before we commit to Mars colonization. The idea that space exploration requires accepting risk is true for astronauts and test pilots who understand and consent to those risks. But if colonization becomes multi-generational, children born on Mars never consented to the risks their parents chose. The generational timeline required for Mars self-sufficiency, if it's achievable at all, means that the project would span multiple human lifetimes. Engineers who designed the first habitats would die long before the colony achieved independence. Children would grow up knowing the colony's success depends on their continued work, inheriting obligations they never chose. This creates a form of generational debt unlike anything in human history. Even multi-generational projects on Earth, cathedrals taking centuries to build, infrastructure projects spanning decades, occurred in environments where subsequent generations could choose to abandon the project without dying. The sunk cost fallacy looms large in discussions of Mars colonization. Once substantial resources are committed, billions or trillions of dollars, years of work, perhaps lives lost, there will be enormous pressure to continue even if the project is failing. Organizations, nations, and individuals will find it psychologically difficult to admit that the investment was wasted. This could lead to pouring more resources into a failing endeavor when honest assessment would recommend cutting losses and pursuing alternatives. Historical examples abound of major projects abandoned after substantial investment, when circumstances changed or problems proved insurmountable. The superconducting supercollider, partially built in Texas at a cost of $2 billion, was cancelled in 1993 when projected costs ballooned and political support collapsed. The Shoreham nuclear power plant on Long Island was completed but never operated commercially, eventually decommissioned after 29 years and $6 billion in costs. These examples remind us that starting a project doesn't obligate us to finish it, regardless of changed circumstances. Mars colonization advocates sometimes argue that the difficulties are precisely the point, that humanity needs grand challenges to inspire greatness, that solving Mars colonization problems will drive innovation benefiting Earth. There's historical precedent for technological spin-offs from space programs: satellite technology, miniaturized electronics, advanced materials. But the logical leap from space exploration produces useful technology to we should colonize Mars doesn't follow. We can pursue innovation directly by funding research into specific problems, renewable energy, medical technology, artificial intelligence, without the overhead of maintaining humans on Mars. The return on investment for Mars colonization, in purely economic terms, would likely be negative indefinitely. Unlike historical colonization efforts that eventually became profitable or independent, Mars colonies would remain dependent on Earth for critical resources for the foreseeable future. The transport costs, the need for continuous resupply, and the lack of valuable exports create a situation where Mars colonies are permanent economic drains rather than investments that eventually pay returns. Some argue that we can't put a price on survival of the species, that Mars colonies are insurance worth any cost. But this argument assumes Mars colonies could survive without Earth, which we've established is unlikely for decades or centuries at minimum. It also assumes that species survival requires physical separation across planets rather than redundancy, resilience, and sustainability on Earth, preventing extinction risks on Earth, asteroid detection and deflection, pandemic preparedness, nuclear weapons reduction, climate change mitigation would cost far less than Mars colonization and provide more reliable protection. The concept of existential risk needs careful examination. Truly planet-sterilizing events are rare on human timescales. Large asteroid impacts like the one that killed the dinosaurs 66 million years ago occur roughly every 100 million years. Supervolcanic eruptions cause severe climate disruption but don't typically sterilize the planet. Nuclear war would be catastrophic, but survivors in Southern Hemisphere nations might rebuild civilization. Climate change threatens ecosystems and could collapse modern civilization, but wouldn't eliminate all humans. Most existential risks we face are either preventable or wouldn't be survived by Mars colonies dependent on Earth support. The one scenario where Mars colonies might outlive Earth is a very long-term astronomical event, the Sun eventually expanding into a red giant in about 5 billion years. But on these timescales, Martian colonies wouldn't provide refuge. Mars would become uninhabitable too, as the Sun's luminosity increases. Genuine long-term species survival requires either interstellar travel, which makes Mars colonization look trivial by comparison, or accepting that species, like individuals, have finite lifespans. The biological constraints on Mars colonization are among the most fundamental and possibly insurmountable. Human biology evolved over billions of years in Earth's specific environment: 1 g of gravity, atmospheric pressure at sea level, protection from radiation, 24-hour day-night cycles, specific ranges of temperature and humidity. We're adapted to Earth at a deep, cellular level. Asking whether humans can thrive on Mars is like asking whether tropical fish can thrive in a desert. Technical solutions might keep us alive temporarily, but thriving, reproducing, raising healthy children, living full lifespans without debilitating health problems is questionable. The radiation problem in particular might have no practical solution. You can shield against radiation with mass, meters of regolith, water, or other materials, but you can't shield against secondary radiation produced when primary cosmic rays hit shielding material and create cascades of particles. You can't shield against neutrons produced by cosmic ray interactions without creating more radiation in the process. Active shielding using magnetic fields requires enormous power and creates other problems. The only truly effective shielding is a thick atmosphere and magnetic field like Earth's, and Mars has neither and cannot be given them with foreseeable technology. Recent studies of Apollo astronauts, the only humans to leave Earth's magnetic field protection, found elevated cardiovascular disease rates, possibly linked to radiation exposure during their brief lunar trips. They spent days beyond Earth's protection, and some show health effects decades later. Mars colonists would spend years or lifetimes exposed to even higher radiation levels. The cancer rates, the genetic damage, the shortened lifespans would make Mars colonization a death sentence delivered slowly through accumulated radiation damage. Galactic cosmic rays, high-energy particles from supernovae, are particularly insidious because they can't be blocked without unrealistic amounts of shielding. Solar particle events during solar storms can be predicted and colonists could shelter in protected areas, but galactic cosmic rays are constant and unavoidable. The radiation assessment detector on Curiosity measured doses that would give a Mars surface colonist about a 60% higher risk of developing fatal cancer compared to staying on Earth. This is using current risk models, which might underestimate effects of chronic low-dose radiation exposure. The psychological resilience required for Mars colonization is probably beyond most humans. Antarctica winter-over crews, submarine crews, and ISS astronauts are selected from among the most psychologically robust individuals and receive extensive training. Even so, incidents occur. A Mars colony would need hundreds or thousands of people, and you can't screen everyone perfectly. Personality conflicts, mental illness, criminal behavior, all the problems of human society on Earth would occur on Mars, but with fewer resources to address them and no possibility of removing problematic individuals from the community. The governance model for Mars colonies would likely evolve into something authoritarian by necessity. In an environment where mistakes kill people, where resources are scarce, and where everyone's survival depends on everyone else performing their duties, individual freedom would necessarily be constrained. You couldn't allow colonists to quit jobs they dislike, refuse assignments, or pursue personal interests at the expense of colony maintenance. The colony would require discipline and cooperation at levels that free societies don't usually achieve voluntarily. This doesn't mean Mars colonies would necessarily be dystopian, but it does mean they'd be fundamentally different from democratic societies on Earth. Some science fiction, like Kim Stanley Robinson's Mars trilogy, explores these tensions thoughtfully. The struggle between corporate control, scientific autonomy, and individual freedom in Martian settlements. The reality is that whoever funds the colony would likely control it, at least initially, and colonists would have limited recourse if they disagreed with decisions because they can't simply leave. The timeline for achieving true self-sufficiency on Mars, where the colony could survive indefinitely without Earth support, is measured in centuries at minimum, possibly millennia. You need to progress from basic survival to growing all your food, manufacturing all your equipment, training all necessary specialists in colony-based institutions, and developing a complete industrial base. Earth took thousands of years to develop this complexity. Even with knowledge transfer from Earth, developing it on Mars while dealing with hostile conditions would take many generations. During this centuries-long bootstrapping process, the colony remains vulnerable to single points of failure. If the one machine that produces critical components breaks and can't be repaired locally, colonists must wait years for a replacement from Earth, if Earth is still sending supplies. If a pandemic sweeps through the colony, they might lack the medical expertise or facilities to handle it. If a solar storm damages critical infrastructure beyond repair capacity, the colony could fail completely. These vulnerabilities don't decrease linearly with colony growth. They persist until true redundancy and self-sufficiency are achieved. The cultural evolution of Mars colonies would be fascinating but potentially troubling. Cut off from Earth by distance and communication delays, developing their own identity and culture is inevitable. Within a few generations, Mars-born individuals would outnumber Earth emigrants. These Martians would have no personal experience of Earth, would be adapted to Martian gravity and possibly unable to visit Earth, and would likely develop distinct values, priorities, and worldviews. This cultural divergence could be enriching, human diversity increasing, or could create conflicts between Earth and Mars civilizations. Some science fiction envisions Mars eventually declaring independence from Earth, leading to interplanetary conflict. While this seems far-fetched given how dependent Mars colonies would be on Earth, the psychological dynamics of colonization, resentment of control, desire for autonomy, distinct identity formation, could create tensions. History shows that colonies often seek independence from mother countries, sometimes violently. Would Martian colonists, after generations of hardship building their world, accept Earth corporations or governments controlling their lives? The environmental engineering required for Mars self-sufficiency goes beyond what we've ever attempted. Creating closed-loop life support where waste is recycled into resources with near-perfect efficiency is extraordinarily difficult. The ISS recycles about 93% of water, which is impressive, but still requires periodic resupply. For Mars colonies, that remaining 7% represents water that must be mined, processed, and purified, a continuous requirement that can't easily scale to support thousands of people. Nitrogen is particularly problematic. Earth's atmosphere is 78% nitrogen, essential for proteins and nucleic acids. Mars's atmosphere is 2.6% nitrogen, about 40 times less abundant. Extracting enough nitrogen to support agriculture and maintain habitable atmospheres would require processing enormous volumes of Martian atmosphere. While not impossible, it's another continuous energy and resource demand adding to the colony's overhead. The concept of minimum viable population for genetic diversity adds another constraint. Small, isolated populations face inbreeding depression, reduced fitness due to increased homozygosity. The minimum population size to avoid this over multiple generations while maintaining genetic diversity is debated, but estimates range from several hundred to several thousand individuals, depending on assumptions about reproduction patterns, lifespans, and genetic screening. A Mars colony would need to reach this minimum size relatively quickly to ensure long-term viability, requiring either very large initial populations or rapid population growth, both of which multiply the costs and challenges. Childbearing would likely be encouraged or even mandated in early Mars colonies to quickly reach minimum viable population. This raises ethical concerns about reproductive freedom and bodily autonomy. Would colonists accept pressures to have children for the colony's survival? What happens if infertility rates are higher due to radiation exposure or other Mars-specific factors? What if children born on Mars have significant health problems? These social and ethical challenges compound the technical ones. The educational requirements for Mars colonists are daunting. Every colonist would need to be highly skilled, engineers, scientists, doctors, technicians, because there's no room for specialization that doesn't contribute to colony survival. There would be no artists, philosophers, historians, or professional athletes unless they also had critical technical skills. This would create a society very different from Earth, potentially intellectually impoverished despite high technical competence. Human societies need diversity of thought, culture, and purpose to be psychologically healthy. Eventually, if colonies grew large enough, specialization could emerge, allowing some individuals to pursue non-technical vocations. But this would require populations of thousands or tens of thousands, supported by robust infrastructure and resource abundance that would take many decades or centuries to develop. The interim period, generations of colonists living in cramped, dangerous conditions while working constantly to maintain life support, would test human endurance in ways we've never experienced. The comparison to historical frontiers breaks down when we consider the time to self-sufficiency. American colonies took decades to become somewhat self-sufficient, but remained dependent on transatlantic trade for many goods. They succeeded because the environment, while challenging, was fundamentally hospitable. Breathable air, drinkable water, farmable land. Mars offers none of these. It's more analogous to attempting to establish permanent settlements in Antarctica, which nobody has seriously proposed, despite Antarctica being vastly more accessible and habitable than Mars. As we reach the end of this exploration, we must confront the central question: should we attempt to colonize Mars? Not can we, which is technically possible if we're willing to accept enormous costs and risks, but should we, which is a question of values, priorities, and wisdom. Every dollar, every hour of human effort, every piece of technology devoted to Mars colonization is unavailable for other purposes. Opportunity costs are real, and in a world with finite resources and pressing problems, choices matter. The dream of becoming a multiplanetary species is inspiring. It speaks to something deep in human nature, the urge to explore, to expand, to ensure our survival. But dreams must be tempered by reality. The universe is governed by physical laws that don't bend to our wishes. Mars is a radiation-blasted, freezing, airless desert that will never be truly hospitable to human life as we know it. We can survive there with sufficient technology and support, but we'll never thrive in the way we do on Earth. The resources required for Mars colonization, trillions of dollars, decades or centuries of effort, thousands or millions of human lives spent in hardship, could instead address urgent challenges on Earth. Climate change threatens to disrupt civilization and cause suffering for billions. We could deploy renewable energy, develop carbon capture technology, restore ecosystems. We could solve water scarcity, eliminate hunger, cure diseases, and extend healthy human lifespans. We could establish sustainable practices that let Earth support humanity indefinitely. Near-Earth space offers opportunities that make more sense than Mars colonization. Orbital infrastructure, space stations, manufacturing facilities, solar power satellites, leverages the advantages of space while remaining close to Earth. The Moon provides a testbed for off-world settlement without the communication delays and isolation of Mars. Asteroid mining could provide resources without fighting gravity wells. These nearer-term goals provide stepping stones toward eventual deep space capabilities without committing to the massive undertaking of planetary colonization. Perhaps the most profound realization from this analysis is that Earth is precious beyond measure. It's the only place in the universe we know with certainty can support human life, not just survival, but flourishing. It has breathable air, drinkable water, a protective atmosphere, and magnetic field, moderate temperatures, abundant resources, and a biosphere that evolved alongside us. We are adapted to Earth in every fiber of our being, and no other world we've discovered can offer even a fraction of Earth's hospitability. The images from our Mars rovers, Sojourner, Spirit, Opportunity, Curiosity, Perseverance, show an alien landscape of stark beauty. The rusty soil, the distant sun, the thin atmosphere creating purple twilight skies. It's magnificent and worth exploring robotically. We've learned that Mars once had flowing water, a thicker atmosphere, and possibly conditions suitable for life. We've discovered complex geology, evidence of volcanic activity, and hints of subsurface water ice. Each discovery expands our understanding of planetary evolution and potentially the origins of life. But looking at those images should also instill appreciation for Earth. The blue skies, the green forests, the oceans, the breathable air we take for granted, these are treasures. Earth didn't have to be this way. It could have evolved like Venus, with crushing atmospheric pressure and temperatures hot enough to melt lead. It could have lost its atmosphere like Mars and become a frozen desert. Instead, through a combination of favorable orbital distance, planetary size, geological activity, and perhaps luck, Earth became a paradise uniquely suited to life. The astronauts who've seen Earth from space often describe a profound shift in perspective, the overview effect. Seeing our planet as a fragile blue marble against the blackness of space, with no borders visible, all of humanity sharing one world, creates deep appreciation for our home and concern for its preservation. Perhaps we don't need to colonize Mars to gain this perspective. Perhaps studying Mars, learning about its fate, and how it lost its atmosphere and water teaches us to value Earth and motivates us to be better stewards of the world we have. The future of humanity might not involve planetary colonization at all. We might develop technologies that make physical presence unnecessary, virtual reality, consciousness uploading, or other solutions we can't yet imagine. We might focus on creating sustainable, fulfilling lives on Earth while exploring the universe through increasingly sophisticated robots and AI. We might build orbital habitats that provide Earth-like conditions in space without requiring planets. The assumption that our future must include living on other planets might be a failure of imagination, not vision. Mars will always be there. It's not going anywhere. If we solve Earth's problems, develop the technologies needed for true space infrastructure, and create the economic and social systems that can support sustained off-world presence, then perhaps in a century or 2 or 3, Mars colonization becomes feasible. But rushing into it now, driven by individual ambitions or corporate timelines, ignores the sobering reality of the challenges involved and the opportunity costs of resources devoted to this endeavor. The scientists, engineers, and dreamers working on Mars technologies are not villains. They're often brilliant, dedicated individuals motivated by genuine passion for space exploration. Their work advances human knowledge and capabilities, but we must distinguish between useful research, incremental progress, and responsible planning versus unrealistic timelines, overpromising, and potentially wasteful deployment of resources. We can support Mars research while acknowledging that colonization is not imminent and might never be practical. As you contemplate what you've learned today, I hope you feel not disappointment but clarity. Understanding limitations is as important as dreaming big. The universe is vast, beautiful, and full of wonders we've barely begun to explore. But we explore from Earth, our home, the only world known to harbor life. Protecting and preserving Earth isn't giving up on space exploration, it's recognizing that our planet is the foundation from which all our cosmic ambitions must be built. Thank you for joining me on this realistic assessment of Mars colonization. I know it challenges popular narratives and might disappoint those who dream of Martian cities, but I believe honest, evidence-based analysis serves us better than comforting fantasies. The universe doesn't owe us habitable planets beyond Earth. We have one world that suits us perfectly, and protecting it should be our highest priority. Keep looking up at the stars, keep asking questions, and keep learning about our cosmos. But also look around at Earth. the forests, oceans, mountains, and skies that make our planet unique. Remember that you're made of stardust, atoms forged in dying stars billions of years ago, assembled into a conscious being on this remarkable world. Your cosmic address isn't just Earth, it's the only place in the universe where you can truly thrive. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Will humans ever reach the light speed? In this video, we'll break down the energy requirements, the dangers of cosmic radiation, interstellar dust, and much more. See you there.